Welcome everyone to the Barcelona Mathematics and Machine Learning Colloquium Series. This is an activity organized by the Department of Mathematics of the University Autónoma of Barcelona, but our aim is to share this experience with all the Barcelona universities and research centers, as well as with the global community. So let me give a warm welcome to everyone who join us from many institutions all around the world. In this activity, what we want to address are essentially two questions. What are the mathematics behind machine learning? And what can machine learning do for mathematicians? We'll do that in 3 colloquia. We'll try to keep this periodicity 3 times a year. We'll do it online. And you have all the information on our website and also how to register. We'll have talks plus discussion, but questions are welcome at any time. So we want to make it interactive. You are welcome and encouraged to use either the chat to post your questions or raise your hand, and I will keep an eye on both to let the speaker know. And the most important part is who, and this year we have Marc Lackenby, Elizabeth Manch, and Jürgen Jost. And we'll speak on February, March, and April. All the information again is on the website. So let me just start as soon as possible with the math and introduce today's speaker, Marc Lackenby from the University of Oxford. He is a very well-known, very prestigious topologist, but very recently he made it to the cover of Nature with an article about AI-guided intuition for mathematics. So Marc, thanks a lot for accepting our invitation and joining us, and the floor is yours.
Great. Well, thank you very much indeed for that invitation. It's a real pleasure. So let me just start sharing my screen. Can you see that?
Yes.
Great. Excellent. Okay. So I'm going to be talking about some work that went into the Nature article about how machine learning can be used as a tool for mathematicians, can help us find new patterns in mathematics and to formulate mathematical conjectures. Just before I go any further, I just want to say, just reinforce Roberto's message that this is supposed to be interactive. So please, I do encourage you to ask questions and to just raise your hand or speak in the chat, and Roberto will stop me and I'll answer those questions. So the aim is to show how machine learning can be used to discover new connections in mathematics and to formulate new mathematical conjectures. So the actual machine learning that went into this project was pretty basic. These days there are lots of different types of machine learning. There's unsupervised learning, supervised learning, reinforcement learning, and increasing levels of sophistication. But what we used was pretty vanilla variant of machine learning called supervised learning. So let me just tell you a little bit about that. I should say this is all joint work with Alex Davies, Andras Juhas, and Nenad Tomasev. So Alex and Nenad are both at DeepMind, and Andras is my colleague in Oxford. So what's supervised learning? So in supervised learning, you suppose that there's some subset S of Rn and some function f, which goes from S to Rk. And the idea is that you can compute this, but you don't know the function explicitly. And I'll give you a classic example of such a function f shortly. And you're given various data points, V, in your domain S, as well as their images f of V. And the machine learning algorithms, what they do is they provide a a function capital F, which is defined from Rn going to Rk, that's an approximation to little f, at least at the given data points V. So the way that I view this, and I think is really, this is like nonlinear regression. So in linear regression, you're also given a whole load of data points V and images f of V, and you're expected to come up with a function capital F, which is an affine function, which is the best fit to those V and f of V, those data points. In supervised learning, in machine learning, you're also trying to find a good function capital F that fits the data, but it's usually a highly nonlinear function. So I view this as nonlinear regression. But there are two caveats that distinguish it from linear regression. The first thing is that in linear regression, you get an explicit affine function out. In our case, you don't get an explicit output function, capital F. It's just some function that's defined using this neural network. And what you can do is you can input input vectors W into that neural network, and the neural network will give you your output capital F. So it's not in any way explicit. You could say it's explicit in the sense that you own the neural network and it's there in front of you, but in terms of any kind of explanatory power, it's extremely limited. So that's one of the main differences between linear regression and sort of nonlinear regression. Sort of the difficulty here is a classic problem that although you can compute your function capital F, you don't really understand what it's saying explicitly. The other big distinction between linear regression and supervised learning is that with linear regression, you get a guarantee that your affine function that you've created is, in some sense, the affine function that best fits the data. In sort of the classic two-dimensional case, you have your line of best fit. Whereas here, you have no guarantee that this is the case. There's no kind of certificate that says that capital F is in any way the best possible function, or really you can't really say that it's that good. There are some measures of it, but it's certainly your degree of confidence in how good capital F is not nearly as robust as in the linear case. But nonetheless, this is a extremely useful, powerful tool. So let me give you an example, which is the analysis of images. So you're dealing with a function little f from r to the n to r to the k. So in this example, n is just, say, the number of pixels of an input picture. And you input your picture, say in grayscale, as just a vector then in Rn, where each coordinate just measures the degree of light or dark of that particular pixel. And then you have this function little f, and now little f is going to go from Rn to, just in this case, the reals. So the target space is just one-dimensional in this case. And this, as I say, you're given this function, but you don't know it explicitly. And this is the function that you consider, where f of v is -1 if you have a picture of a cat, 1 if you have a picture of a dog, and say 0 otherwise. So I think most people would agree in some sense that is a function. It's certainly not a typical mathematical function, but it's nonetheless in some sense a function. And we can compute it, but we certainly don't know it explicitly. And then you feed that into your machine learning algorithm. You give a whole load of data points. So in that case, it's a whole load of pictures of dogs, cats, and maybe other things too, and you say for each one whether it is a dog or a cat or something else. And that's why it's called supervised learning, because some poor person has to actually give the neural network that information. It requires supervision by a human. But then the neural network then learns this function capital F, and that means that when you can give it, you give the neural network some other picture as encoded by a vector W, it'll give you an output, capital F of W. And that'll hopefully be close to -1 if it's pretty sure that it's a picture of a cat, and close to 1 if it's pretty sure if it's a picture of a dog, and hopefully close to 0 if it's somewhere in between, uncertain. So that is your classic example of supervised learning. Okay, so our goal was to use supervised learning in mathematics, and it was designed, we hope to try to discover new connections. So let me explain what the project was. So this was in knot theory. Knots are just simple closed curves, smoothly embedded in 3 space. And the idea of knot theory is to, has many goals, but one of the primary ones is, in some sense, to form a classification of knots. To be able to decide whether 2 knots are the same or not. In other words, one can be deformed into the other. And there are many, many different ways of tackling knot theory. One of the real attractions of knot theory is that it's highly connected with other areas of mathematics. So, for example, it relates to quantum field theory, it relates to non-Euclidean geometry, it relates to algebraic geometry, it relates to statistical physics. There are now many interesting connections from knot theory to many other areas of mathematics. And as a result, there are now many different branches of knot theory. So there's hyperbolic knot theory, which is concerned with the hyperbolic structures that exist on many knot complements. So I'll tell you a lot more about hyperbolic structures later in the talk. There's gauge and Floer theory, which is inspired sort of initially by the work of Donaldson, Simon Donaldson. It deals with things like instantons and Heegaard-Floer homology, and it comes from a very different area of mathematics. And then there's quantum topology. Quantum topology was essentially established in knot theory with the introduction by Vaughan-Jones of the Jones polynomial. So the Jones polynomial is a Laurent polynomial attached to any given knot. And now there are many other different invariants in the area, things like Kovanov homology or the quantum SU2 invariants. There are Vasiliev invariants. There are many other different quantities that one can now attach to a knot of increasing complexity that fall under the realm of quantum topology. So these are 3 very different areas of knot theory, and they are not very well connected. So there are some connections that are beginning to be understood between the second and the third areas, namely between gauge theory and quantum topology. Specifically, Kronheimer and Mrofka showed that there was a connection between instanton homology and Kovanov homology, which are quantities that lie in the second and the third areas. And that has some important consequences. But certainly the first area, hyperbolic knot theory, which is really the area that I work in, is quite poorly connected to the other 2 fields. So to illustrate this, here are some lists of speakers from 2 conferences that happened last summer. So on the left-hand side, you have the speaker list at Alan Reed's conference. Alan is a hyperbolic geometer, and there you have a list of speakers at his conference. And on the right-hand side, you have a conference that happened in Trieste about a month later, and you can see the themes of the conference. It's the interplay of three-dimensional and four-dimensional topology, Floer homology theories, and associated invariants, Koganov homology, and geometric and analytic aspects of gauge theoretic equations. So the reason I mention this is that the first left-hand side is the first area of knot theory that I highlighted, and the right-hand side is the second and the third areas. And you can see here that this list of speakers are disjoint. There's no one who spoke at both conferences, and that kind of highlights how divided the field is. So our goal was to try to discover new connections between these different areas. That was our goal. And how do we do it? Well, we looked at the invariants that were associated with each of the different areas. So on the hyperbolic side, the hyperbolic structures, as I say, are what they are, the Riemannian metrics on the complement of the knot. So there are lots of Riemannian invariants that you can attach to such a thing. So, for example, the volume of the metric, or the cusp shape and volume, and I'll talk more about that later. Or the length spectrum, which is the lists of the lengths of the geodesics. There are all sorts of interesting quantities attached to the hyperbolic structure. And then on the other side, there are things like Heegaard-Floer homology, instanton Floer homology, S and tau, epsilon, upsilon, lots of different Greek letters attached to such things. But we actually focused on a classical invariant called the knot signature, and I'll talk very shortly about what the knot signature is. But it definitely lives on this other side. As I say, our goal was to find connections between these invariants. And why? Well, one is so that we can have more harmonious conferences where all these different mathematicians can go to at the same time. But other reason is to try to use information from one area and port that across to provide information about another area. So in particular, on the right-hand side, these are not just three-dimensional invariants where the knots live, but in some sense they're also four-dimensional invariants, and you get four-dimensional information. And I'll tell you exactly what I mean by that shortly. But on the left-hand side, the hyperbolic structures, these are not well known to be connected to anything four-dimensional. So if you find a connection between these different areas, then you potentially can use information from one to give information about the other. Okay, so let me just briefly tell you about what the knot signature is, and then I'll come back to how the machine learning worked. So the knot signature was the three or four-dimensional invariant that we looked at. So it's defined as follows. So you've got your knot sitting inside three-dimensional space. And one of the things that you can do with knots is you can always find a Seifert surface for them. So a Seifert surface is a compact oriented surface sitting inside three space whose boundary is the knot. Okay, so classic example of a very simple Seifert surface is if I have the unknot, which is a round circle, and that bounds a disk. And that disk then is a Seifert surface for that knot. But you can get more complicated surfaces. For example, I could have taken that disk and added on a little handle to it, and that would still be a Seifert surface. So it turns out you can always pick a Seifert surface for the knot. It's not unique. And then there's an associated bilinear form on the first homology of that surface. So it takes as input two elements of first homology and it spits out an integer. You represent those two elements of first homology as loops, L1 and L2. sitting inside the surface. And then you form L2 plus, which is you just push off L2 in the transverse direction, because there's a well-defined normal direction to my oriented surface. And now you've got L1 and L2 plus, which are disjoint. So you can form their linking number. So that's the first term. And if you just look at the first term, is what's called the Seifert form. And it's used to define, for example, the Alexander polynomial of a knot. But we symmetrize it in this situation here, reversing the roles of L2 and L1. And that forms a symmetric bilinear form. And when you've got a symmetric bilinear form, you can look at its signature, which is you just realize it as a square matrix and look at the number of positive eigenvalues minus the number of negative eigenvalues. And it turns out that that is an invariant of the knot. So it's a classical invariant. It was defined in the mid-20th century, and it's as I said earlier, it has these four-dimensional applications. So how does four dimensions come into this? Well, you have your knot sitting inside 3 space. Here's such a knot. And you view R3 as the boundary of R4 plus. So R4 plus is upper half space in R4. And then you consider surfaces in R4 plus that the knot bounds. So if the surface had been sitting inside R3, it would have been a Seifert surface. But we allow our surfaces to go into R4 plus. And so you could talk about the four-ball genus of a knot to be the minimal possible genus of a surface in R4 plus with boundary equal to that knot. So it turns out that actually this number can be 0 even when the knot is non-trivial. So in particular, actually for this particular knot that I've drawn here, it actually bounds a disk in R4 plus. And so its four-ball genus is 0. But there are some knots who have positive four-ball genus. In other words, they don't bound disks in R4 plus. And this four-ball genus is a really important quantity. So, for example, in Friedman's proof of the topological four-dimensional Poincare conjecture, in some sense, the key to the proof was knowing that certain knots have four-ball genus 0. So this quantity is something that four-dimensional topologists really care about. And it's related to the signature by a theorem of Murasugi, who proved that the four-ball genus is at least half the absolute value of the signature. So in particular, if the signature of a knot is non-zero, then that means the four-ball genus has to be strictly positive, and so that means that it cannot bound a disk in R4 plus. Okay, so that gives you one side of the story. This is one of the invariants that we looked at, the signature, and it's a pretty crucial central invariant, and it relates to the four-dimensional topology. Okay, so how did the machine learning come in? So the goal we set ourselves was try to find an answer to this question. Can we predict the signature from the hyperbolic invariants? So there's this long list of hyperbolic invariants, things like volume, cusp shape, etc., etc. Do they control the signature? In other words, is there some function, little f, which takes as its input the hyperbolic invariants of a knot? And these invariants are typically real-valued invariants, things like volume or the length of the shortest geodesic or the cusp area or things like that. And if they're not actually already real-valued invariants, you can often turn them into real-valued invariants. So plug in these hyperbolic invariants of your knot, and you ask, can they do they determine the signature? In other words, is there a function little f from Rn which contains the hyperbolic invariance of the knot to R that outputs a knot's signature? And we're not necessarily looking for it. I mean, ideally we would, but not necessarily looking for it on the nose. We're looking maybe just for a good approximation to it. Okay, so this has been then phrased in the framework of supervised learning, which is asking, you know, where supervised learning is exactly the setup where you have some function little f. So what we then did was we then created a data set of 2.7 million hyperbolic knots. And fortunately, there's this wonderful computer program called Snappy, which allowed us to create this set of knots. So in particular, there's it contains a census of knots up to a certain number of crossings. So we looked at all knots up to almost 16 crossings, of which there are about 1.7 million of them. And we also looked at 1 million randomly chosen knots. So Snappy has this interesting function where you just click random knot, I think it is, and it spits out a random knot diagram. And in some sense, it's genuinely random. It actually relies on the theory of quadrangulations of the plane, which is this fascinating branch of modern probability theory to sample uniformly at random from a set of possible link diagrams. I'll come back later in the talk as to how important it is to get these data sets right. In fact, one of the really important aspects of the use of machine learning in this area is to choose your data sets well. And actually, random is not necessarily good. So then what you do in supervised learning is you divide your set into two groups, a training set and a test set. And then you use the training set to train your neural network. And you give it the data points, which consist of V, which are the hyperbolic invariants of your training set of knots, and F of V, the signature. And you see if your neural network can learn to predict F of V. And you test that then against the test set. And you see how well it does. And the answer is it did remarkably well. Okay, so you can actually measure this in terms of, for example, how often is it within, is the closest integer to F of V, the actual signature. And it was getting the answer right an incredibly common number of times. And so then we knew that we were onto something. Right? This is saying that you can predict the signature from the hyperbolic invariance of the knot. And so there is probably some function little f. Right? So this was not obvious from the outset. If there had been no way of predicting the signature from the hyperbolic invariance, if there'd been no connection between these two areas, then no matter how good your neural networks, no matter how clever your collaborators at setting them up, there would be no way of being able to predict the signature from the hyperbolic invariance. So the fact that the network could do this was showing that there really was likely to be some function little f there. So we thought, right, excellent, machine learning has provided us new information. Now we need to go away and find out what this connection is. And at this stage, you hit a problem. And the problem is that machine learning does not want to tell you what the function capital F is. Right? It's hidden within this super complicated neural network. And what you'd like to have is some more simple relationship that relates the hyperbolic invariance to the signature. So this is a classic problem in supervised learning and machine learning more generally, is the question of interpretability. But fortunately, there is a tool. So there's something called saliency, which what it does is it tells you what the main input features are that the network is using to compute capital F. So this is actually it's actually a very simple thing, right? Now you've got your function capital F, which is the function defined by this neural network. And now you just take your input points and you just wiggle them a little bit. And now when you wiggle them a little bit, you're changing your vector in Rn. It no longer necessarily corresponds to the list of invariants of a knot, but doesn't matter. So you wiggle your input vector a little bit, and you see how that affects the answer. And you have to make sure that your input sort of suitably normalized. That's what this normalized attribution score is all about. But you can see that the output is these bars. It can tell you what features it's using. And here it's pretty clear that there are three main input features that it's using. So this is just a list of the top 10, but we input maybe 30 features. And it is clear that these three are the main ones that the network's using. So they are the imaginary and real parts of meridional translation and longitudinal translation. And I'll tell you more about what these quantities mean in just a bit. So we now thought, yes, we are pretty much onto something here, that it seems that the signature is determined by just these three quantities, or at least determined up to a good approximation. And for me, as a hyperbolic geometer, I was very surprised by this, because these three quantities, they're all in the same family. They're all encoding what are called the cusp shape of the knot. And I'll tell you about what that is in a bit. But it was very striking to me that the cusp shape is completely encoding the signature. Okay, so let me tell you about what hyperbolic invariants are, because otherwise, yeah, this is just talking about names. I want to try to give a feel for what these quantities are. So a hyperbolic structure, what you do is you take your knot, you drill it out, and the resulting object is a three-dimensional manifold, the knot complement. And then a hyperbolic structure is a Riemannian metric on that knot complement, which is complete, has finite volume, most importantly, has constant curvature -1. That means it's locally isometric to hyperbolic space. Now, it turns out, it's long been known that if there is such a metric, then it's unique up to isometry. And the important thing about that then is that metric invariants like volume are then just invariants of the knot. And it's known that most knots have such a hyperbolic structure on their complement. So Thurston proved that a knot has a hyperbolic structure on its complement if and only if it's not one of these two types. So here on the bottom right, it's a torus knot. So by definition, the torus knot is one that can be drawn on the standardly embedded torus in 3 space. So it's just determined by two numbers, P and Q, which just measure how many times the knot winds around each time around the meridian and longitude of the torus. And so those don't have hyperbolic structures. And also satellite knots don't. So here's a satellite knot. In a satellite knot, what you do is you take a non-trivial knot, in this case, trefoil, and then you thicken it up to form a solid torus. And then within that solid torus, you put a new knot, and that's your satellite knot. And there are two basic conditions that it must satisfy. It mustn't live inside a 3-ball within the solid torus. It's really got to go all the way around the solid torus. And it mustn't be a core curve of the solid torus either, because then it really wouldn't be a non-trivial satellite. And Thurston's theorem, this is what Bill Thurston basically got his Fields Medal for, says that as long as you're not these two types, then you have a hyperbolic structure. And so, as I say, there are these three quantities. You can associate many different quantities to a hyperbolic structure, but there are these top three, meridional and longitudinal translation. They're real and imaginary parts, which seem to control the signature. And those are related to so-called cusp geometry. So you have this metric on your hyperbolic, on your knot complement. And at the end of the knot complement, there's torus cross half open interval, right? So you've drilled out your knot, so you've got something non-compact now. And it has an end which is sort of surrounded by, you can surround this knot by this torus, and then you can think of larger or smaller tori which are enclosing your knot. So that gives you a one parameter family of tori which are at the end of your knot. And so you get an end of the form torus cross half open interval. And that has a canonical geometry called a cusp. And let me just quickly tell you about that. You take the upper half space model of hyperbolic space, and you look at the set of points with z coordinate greater than or equal to 1, call that h. And then you act on h by a z plus z subgroup, z plus z group of Euclidean translations. And a fundamental domain for that action is just given by, well, in each level, it's just given by a parallelogram. And so you just take parallelogram cross half open interval, and you glue opposite sides under the action, and that gives you torus cross half open interval. And the geometry on that thing is your cusp. So typically what we try to do is take what's called a maximal cusp, which is where you try to expand this end out as far as possible into the manifold, and you do that until it just bumps into itself. And that's called a maximal cusp. So the boundary of that maximal cusp is given by a parallelogram with side identifications. In other words, a Euclidean torus. And curves on your torus, they're just represented by Euclidean geodesics. So this torus is just running along the knot. And so there are two natural curves on that torus. There's a meridian, which just encircles the knot. And there's a longitude, which runs once around along the knot, and that has 0 linking number with the knot. Okay, so those are sort of a canonical choice of generators for your lattice, Z plus Z lattice. So you can view this torus as the complex plane quotiented out by your lattice lambda, and you just kind of rotate it around so that one of the corners of your parallelogram is at 0, and the longitude, which is the curve that runs along the knot, corresponds to a real number, and the meridian corresponds to a complex number with positive imaginary part. And so SNAPPy, this program that I was talking about earlier, it provides you this information. It provides you a long list of hyperbolic invariants, but this is an actual output from SNAPPy. So here you can just draw in a knot. This is the knot 6-1, it turns out. And it'll give you this output. It'll give you this parallelogram. So there are two complex numbers, lambda and mu. Lambda has been arranged to actually be real. And then mu, you can look at its real and imaginary part. So you end up with a list of 3 real numbers, which are encoding the geometry of this torus. And those 3 numbers are the main things that the saliency analysis was telling us were controlling the signature. So we now got 3 numbers which control the signature. The question remains how, and for this we use sort of good old-fashioned detective work. And we plotted this plot here. So here, this is a scatter plot. Each of these dots represents a knot. And on the y-axis, you have the knot's signature. The x-axis, you have the real part of original translation. And to provide a little bit of extra information, we then also colored it by the longitudinal translation. So you can see here that something is, as the machine was telling us, something is definitely going on. This is not just some random scatter plot. This definitely has some structure, but it's still not completely clear what that structure is. But one thing you can see from this is that these points, they're mostly concentrated in the top right quadrant and the bottom left quadrant. So what that means is that the signature tends to be positive when the original translation is, the real part of original translation is positive. And they both tend to be negative together. Not always, there's some little stuff going on near the origin, but that tends to be the theme. So it's somehow saying that the sign of the signature is controlled in some sense by the sign of the real part of mu. So remember, mu is this complex number here, right? And so what it's saying is that if the parallelogram is skewed right, the knot tends to have positive signature. And if the parallelogram is skewed left, then it tends to have negative signature. So what we thought was, can we come up with a quantity that measures the skewness of this parallelogram? And we came up with the following quantity, which is we called the natural slope. So it's best, I think, defined geometrically. You pick a geodesic representative mu for your meridian, and then you pick a point on mu and you fire off a geodesic in your torus orthogony, or that mu perp. And then it runs along the torus until it comes back and hits mu at some point. It needn't come back exactly hit back at the same point that it left off. But as it does it, it's gone along the longitude of the knot plus some number of meridians. And that number s is a real number, and that is basically the slope. So we actually define the natural slope to be minus s, and it turns out a little bit of elementary Euclidean geometry says that you can get it from lambda mu as the real part of lambda over mu. So in some sense, this is definitely encoding the skewness of your parallelogram. In the case where your parallelogram, let's just go back, is a rectangle, then mu here is purely vertical. So when we run along something mu perp, we're running exactly along lambda. And so in other words, mu perp then is lambda plus 0 meridians. So the natural slope is 0 exactly when this parallelogram is rectangular. And it's measuring the skewness of the parallelogram when it's positive or negative. So we thought this seemed like a good quantity to look at, and we plotted it then against signature, and you can see here that it's basically a straight line. That slope is on the x-axis, signature is on the y-axis, and basically with some error, signature seems to be linearly related to slope, this new quantity that we defined. So that led us to our first actual mathematical conjecture, that there should be some constant C0 so that the signature of a hyperbolic knot is approximately a constant times the slope. And the data here strongly suggested this. So these horizontal lines, they're not error bars. In some sense, you could view them as error bars. They're just lots and lots of points, lots and lots of knots. Right? This is 2.7 million knots forming this plot. And so you look at that data and you say, yes, surely this conjecture has to be true. Well, as I say to my undergraduates, this little twiddle sign doesn't really make sense. So let's make it a little bit more precise. That says that, so the conjecture, the more precise conjecture says that there are constants C0 and C1. So that the signature minus C0 times the slope, its absolute value is bounded. The error is bounded, and the natural quantity is to bound it in terms of the volume. That's sort of a very good measure for the size of the knot K. Okay, so that was a conjecture, and our data definitely supported it, and we spent a long time trying to prove it, but alas, without success. Eventually, we hit on some reasons why it could not possibly be true. So here's a big theorem, which I won't go into in too much detail, but basically we looked at these examples of knots, which are, what they are is, what you do is you take some sort of template link, which has a knot here and various unknotted curves. And then you have various strings going through these unknotted curves. And then you remove the unknotted curve, but you add in Qi full twists. So Q1 full twists here and Q2 full twists here, etc., etc. And you call the resulting knot K Q1 up to Qn. And these theorems said that actually, well, there are various things you know. One is that the volumes, the error terms, are all bounded for this sequence. The slope you can estimate, and the signature you can estimate. And the crucial thing is that the slope and the signature behave slightly differently. And so therefore they could not be linearly related. And therefore the conjecture that we made was false. And this was a bit depressing because we've been working on this for some time. We had 2.7 million data points that suggested that the conjecture was true, but we found some counterexamples. But fortunately, we got enough insight from this to be able to formulate the correct theorem, which we were in the end able to prove. So the correct theorem is that there's a constant C1, so that the signature and half the slope differ by an error, which is a constant times by the volume times by the inverse cube of the injectivity radius, which is another geometric quantity. And we were able to refine this to a theorem 2, which said that the signature and half the slope plus a correction term differ by, at most, a constant times the volume. And the correction term was defined in terms of short geodesics in your Riemannian metric. So you looked at certain geodesics, and for each one there was some correction term that was defined in terms of its length and its so-called complex length, which also measures how it rotates as you run along your geodesic. And so we were able to say that actually the signature, theorem 2 and indeed theorem 1, say that the signature can indeed be estimated by purely geometric quantities, which is what we hope to prove. So that was sort of the end of the project. We succeeded in setting out to do what we wanted to do. And then here's one of the really interesting things, that we went back and looked at our saliency plot. And you can see there are those three quantities which seem to be controlling the signature. But actually, if you look at the fourth and the fifth, fourth is looking at the imaginary part of the complex length of the shortest geodesic. And the fifth was the injectivity radius, which is also related to the shortest geodesic. And so in some sense, what this is saying is that actually the machine knew all along that actually that the conjecture wasn't quite right, and that actually the fourth and the fifth terms really provide good correction terms to estimate your signature. So in some sense, I guess the moral of the message was that we thought that these lower, smaller error bars were just noise. You get this in your neural networks, that they're defined stochastically. They're not perfect, and so you get errors, you get noise. I mean, that's what we thought was just going on here. But it turns out that the fourth and the fifth terms really are actually kind of crucial, which I think is pretty remarkable. So that's the story, and so we're pretty pleased with how it all worked out, but it's worth emphasizing that there are certainly some difficulties with this method. So the machine learning said that the neural network gave us this function capital F, and we could use saliency to work out what inputs capital F was using most. But it didn't actually provide a formula for capital F. And finding a formula requires human input. So the machine learning shows that there exists some connection, and it provides you some information about what that connection is between these different mathematical quantities. But to actually formulate that as a fully fledged mathematical conjecture requires human input. Another important thing is that, well, this worked because we had a lot of data. You have to be in an area where there's a lot of data. And it was also quite useful that the inputs that we could put into our networks were real numbers, things like volume or the lengths of geodesics, or indeed the three parameters controlling cusp shape. And that's not true of every area, right? So there are lots of areas of mathematics where the quantities that you're looking at aren't real numbers, and it's hard to encode them as real numbers. So that's definitely one thing that helped in our case. Another thing is that machine learning tends to ignore outliers, and this is actually pretty important. That we gave it these 2.7 million data points, which we divided into a training set and a test set. And when it was training, what it tries to do is it tries to come up with something that best fits its input data. But if there are a few data points that don't fit it, then it just tends to ignore them. And that's fine when you're trying to get something that just works lots of times, like trying to find something that can most of the time tell you whether it's a cat or a dog. But as mathematicians, we're trying to find something that's true all the time. And this tendency to ignore outliers is an issue. That said, though, you can flag your outliers. That's certainly something that you can do. You can see which data points where little f and capital F are differing most, but it could be quite hard to interpret those. The other thing is that it's really important to curate your input data. So we gave it this list of all knots up to 16 crossings, and also a list of randomly chosen knots, and we thought that randomly would be a really good idea. But the thing about random choice is that somehow random is not necessarily fully representative of the whole diversity of possible examples. When you take a random data set, it tends to sort of cluster around the mean in some sense. And so it was the fact that in fact, actually, the way we started to find our counterexamples to our initial conjecture was by looking at a third data set, a different type of knots, which are formed by taking grades. And it was only then that we started to see problems in our method. So I guess so that, the moral here is don't necessarily think that random is good. You should be trying to use a genuinely diverse data set to try to get the most power out of these methods. There's something else that I want to say, like just one other example, which, you know, other people have been using these methods and coming up with some really interesting observations. But what I want to show is one example which sort of highlights the difficulty, which is to do with the Jones polynomial. So the Jones polynomial was in this third area of the so-called quantum invariants, and it's a long polynomial attached to each knot. And I think it's fair to say that the Jones polynomial of a knot is a pretty mysterious thing. I mean, you can define it. It doesn't take too long to define it. But what it's really encoding is not at all obvious. And so you can ask as well, it's a really worthwhile question, is it related to other invariants? And so these three researchers tried to do something similar, in fact, to what we did, which was to see if you could predict the hyperbolic volume from the Jones polynomial. So you plug in the Jones polynomial into your network and you see whether it can detect the volume. So very much the same sort of thing that we did, except going, rather than using hyperbolic invariants to estimate something else, to go in the other direction, using input being the Jones polynomial, and see if you can estimate a hyperbolic invariant, in this case, volume. And right, so in some sense, it was already known that this was a good idea, because there's what's called the volume conjecture, which says that the volume of a knot is completely encoded by the Jones polynomial of the knot and its parallels. But just looking about the Jones polynomial of the knot, not its parallels, is what was happening here. And it turns out that the neural network really can predict the volume very well. You can see a similar sort of scatter plot, and it's the network is doing an extremely good job at predicting volume, just knowing the Jones polynomial. So I think this is fascinating. Something is clearly going on here. But what has not been able to be achieved here is the next step, the somehow interpretation of this, the crystallization of this into a fully fledged conjecture. And it seems kind of hard to encapsulate this into a conjecture. So although in our case we were able to, I think this is actually, well, it's an interesting challenge to be able to go from the machine learning to an actual mathematical conjecture, which you have a hope of proving is definitely a non-trivial thing. But I hope that I'll be able to persuade you that actually the machine learning is a useful tool. It does highlight connections that were not known before. And I do hope that it's used by mathematicians to come up with new mathematics. So I'll leave it there. Thank you very much.
Thanks a lot for your fascinating talk and the story, and also keeping this suspense ingredient of, yeah, we are not getting there, and then it was all the time like in the graph. So now it's time for discussion and also questions. I guess there were none because we were all mesmerized by the story, but now we have some time. If someone wants to throw some question directly related to the talk or around the area. Okay, let me do the first one. Yeah, because I guess that's the most difficult one. So how did it all start? What was your experience like? How it came up, this project? Was it your idea? Someone from DeepMind knock on your door? Some collaborator? How was it?
Okay, so yeah, I feel very lucky. It came up from a discussion between Geordie Williamson and the CEO Demis of DeepMind, and they met, I think, at an event at the Royal Society where they were both being inducted in as fellows of the Royal Society, and they agreed that it would be really good to try to use machine learning as a tool for mathematicians. So they started talking. Geordie works in representation theory, but they were also looking for other areas, and Geordie said, well, look, let's do something, maybe do something in knot theory. And his view was that sort of knots might be you know, a relatively tractable area that these sorts of methods might work. And so, yeah, the people from DeepMind reached out to me, and you know, so I feel pretty lucky. And I got my colleague Andras on board because he and I had also been talking about, just coincidentally, about using machine learning as a tool. And so when we were approached by, you know, these, I mean, DeepMind is an incredible company, and the people who work there are extremely talented. And it was just, we were just so lucky to be able to get them on board. I mean, I should say though that was not an easy thing to sort of get off the ground. I think there's a bit of a learning curve that was required for both sides. So, you know, on the one hand, you know, as mathematicians, we're dealing with, there's quite a lot of, you know, background knowledge that we had to impart to our colleagues at DeepMind. Fortunately, they're super clever, and we're able to pick it up in, you know, just weeks, where I was unbelievably impressed. But on the other side, they had to sort of explain to us sort of some of the aspects of machine learning. And I think it's kind of an important, you know, machine learning is an art. It's somehow setting up these networks is not such an easy thing to do. There are a lot of hyperparameters that one needs to specify, and it's like the choice of architecture of the network, the number of layers, that kind of thing. That, as I say, the sort of things that we were using was relatively vanilla, but there are much more sophisticated things that you can do. Knowing what to use is actually, I think, one of the you know, one of the hurdles that mathematicians face in getting into this. That said, though, there are, you know, things that, you know, there are packages that are just available online and that one can get going with. But it really helps to have collaborators who really know what they're doing. Because the problem is, it's, you know, you can, if you set things up wrongly, your network doesn't learn properly, and you don't know why. And you know, there are all sorts of other bad things like overfitting and such, like where in some sense the network learns too well. It kind of learns by heart the data points rather than seeing the pattern. So trying to get deal with these machine learning issues is a non-trivial task, and it really helps to have people who know what they're doing. But it is possible to get into this without having collaborators at DeepMind.
Okay. Someone wants to ask, yeah, we have a question. So Jose, please go ahead.
Okay, thank you, Mark, for your talk. Thank you very much. Just one question about when you talk about not invariants, or I wonder if it should be a question to consider the polyhedral decomposition of, for instance, a link exterior. And then, as you well know, from the augmented link, you can get, by doing then surgery, you can get the knot itself. I don't know, I think that this process of doing then surgery, in this process, you lose some information about the cast shape of the knot. I wonder if this loss is very high. I made some small experiments with Snappy, and it doesn't seem that it's true that you don't lose very much information about the cast shape.
Yeah, right. So I mean, yeah. So there are two things there. One is using the polyhedral structure on the knot complement, and absolutely. So Snappy gives you the canonical polyhedral decomposition, and that was actually one of the things that we fed into the network. So the question is, how do you feed a polyhedral decomposition into a network? And that's a bit of a major design issue. So we actually encoded it in terms of a graph, and, you know, for example, the a graph with, say, encoding the gluing information on the edges, on the faces, so like the dual graph to the polyhedral decomposition, and also encoding like the interior angles of the polyhedral decomposition. And certainly, our thought was, well, look, this polyhedral decomposition encodes everything, right? It completely encodes the knot. It's a complete invariant. And so this should be a really cool thing to stick in to the network to make it, see if it can learn the signature. And well, it turned out it wasn't that good. Like somehow, if you provide a network with like too much information, it can get lost somehow. And so it's really tempting as a mathematician to think, I'm giving the network everything it needs. But actually how you represent data and how well data is encapsulated by a vector, which is effectively your input, is really important. And so that sort of like highlights the difficulties of this method, that actually you want to be really ideally dealing with inputs that naturally come as vectors, as lists of real numbers. So that's the polyhedral decomposition. I think it's a really interesting idea, and let's say we explored it. The relationship with Dane surgery is, as you point out, a very interesting area, and the behavior of the cusp shape as you do surgery on other components is a pretty interesting thing. And actually, that's exactly it. I mean, this big theorem that I wrote down, which was dealing with these knots K, then labeled up to Q1 up to Qn. That's exactly behavior. That's a surgery construction, and so we were looking at the behavior of cusp shape under that surgery construction. So yeah, we were seeing some of the things that you observe, and we were able to encapsulate that as a theorem that controlled how cusp shapes behaved under surgery.
Thank you.
Joan, please go ahead.
Yeah, well, thank you very much for your talk, Mark. Hi, it was really nice. So let me ask just a classical question. So can you say just a very few words why your theorem is true? I know.
Yeah, so I didn't.
I'm worried about, I'm just asking, for instance, about the short geodesics, why they are relevant for this formula.
Yeah,
it's a kind of mystery
thing, isn't it? Yeah. So hey, I had a whole other talk which is available.
Yeah, I know,
but like I thought it wasn't really appropriate. So in summary, what you do is we drill out the short geodesics, shorter than the Margulis constant, and then form triangulation of the thick part using the sort of Thurston construction, where the number of tetrahedra is proportional to the volume.
Yes.
And then in there, find a spanning surface for your link, not necessarily an orientable spanning surface, which intersects each tetrahedron in either just a single triangle or a single square. So it's maybe a non-orientable surface. And then use the so-called, use Gordon and Litherland's formula for signature, which allows you to compute the signature of a knot, not necessarily from an orientable spanning surface, but a non-orientable one. And it turns out that it's like the signature of the Goritz form plus some error term. And that error term is a crucial thing. And it turns out really that is the slope. That's what's coming out as the slope. But then I've drilled out my short geodesics, so I need to put them in, and so we need to understand how signature behaves when you kind of do your surgery back in, and so that's another aspect to it, and that leads to a correction term. So that's it in a nutshell. I could tell you more, but it's actually there's a version of this talk which has the proofs in it and is actually available on my website. So
okay, thank you. No, this was really.
Yeah, it's kind of an interesting thing. Like the story, you see the theorem, you still don't really understand what the story is behind it. It's kind of
right. Okay, thank you.
Yeah.
Okay, if you have questions, just raise your hand. Meanwhile, let me ask what's next. Like because you mentioned somehow this work about the Jones polynomial by other people, but you seem very relieved by the fact that you managed to formulate a simple conjecture and they are just like not managing to like. Yeah,
I didn't want to give that impression. So I have what we so yeah the talk, there's actually some slides beyond this which is on exactly what next. So what we've done is you know ChatGPT, it's based on transformer networks, and it's you know, so these transformer networks, they've been around a long time, and they well, not long, but they're not like that. They certainly predate ChatGPT, and they take as their input natural language. And so what we did was we say, well, let's encode a knot as a closed braid. And a closed braid you can just write down as a word in the braid generators and their inverses. So imagine it's like some long word which you view as natural language. Now input that word into a transformer network and see if you can get it to learn interesting invariants. Say things like, well, we actually were looking at the Jones polynomial, the maximum and minimum degrees of the Jones polynomial. And it turns out, yeah, your transformer network can work out these maximum and minimum degrees. So you may say, well, what's the big deal? Because the transformer network has all the information it needs to get the knot and therefore to compute the polynomial. So it's not quite like what we were doing here, where it wasn't clear that there was a connection. It's clear that the closed braid determines the Jones polynomial. But nonetheless, it's interesting that a network can learn it. Like somehow there's something more something else is going on. And actually, so we formulated this as a conjecture that the maximum and minimum degrees of the Jones polynomial can be read off very simply from the braid word. And yeah, so that's what's next. That's what we're working on next. And I think I've got a chance that one can prove this actually. So this is an example, not where relating two different invariants, but somehow getting an interpretation of an obscure invariant, this Jones polynomial, like what it's really doing in terms of more elementary stuff. So that's what we're working on next. Yeah, but I think that's what we're working on. But I want to try to encourage other people. Like this doesn't have to be a knot theory. This is a very broad. Like this could be used in many different areas of mathematics. So yeah, I want other people to try to run with this.
Okay, just out of curiosity, so how much of your time now you think of your research time you devote to some machine learning related projects and say old-fashioned like the math you used to do before machine learning?
Well, currently I have two big administrative jobs in Oxford. So I think more question is how much am I actually getting to do any research at all? But when I do get to do research, I do a bit of this and quite a lot of classical stuff as well. I've got two big projects which I'm desperately trying to finish off.
Okay. And did you get interested by the math? Okay, how far did you go in trying to understand the math behind machine learning? You were working with DeepMind, who are like probably the best in the world to do that with. So you really didn't need to somehow. I mean, I guess you need it because to know how things are working. But did you get interested in why it is working and so on?
Yeah, well, I did a little bit. It's pretty. I think it's pretty hard to come to a really sound mathematical reason for why it works so well. I mean, other people I'm sure will disagree with me on that, but I still view it as something of a miracle that this stochastic gradient descent works so well on like these. I mean, you're dealing like, with the dog versus cat thing, you're dealing with, your input space is, dimension which is hundreds of thousands or millions, and yet nonetheless it can you can work out this function. Like I think from the mathematical point of view, it's still pretty surprising. Another really interesting thing, and I heard Geordie Williamson talk about this, is that it seems like some of these input functions, little f, are easier to learn than others. Like machine learning is actually really bad at some fairly elementary things. Right? So take this input function, where your list of numbers, your input numbers, they're a vector, but let's say they're just noughts and ones. And let's say the output is the sum of those mod 2. Right? So you just input a whole load of noughts and ones, and we want to say, what's the sum mod 2? Is it naught or 1? Right? So from a mathematical point of view, it's pretty trivial. Like the best networks can't do this. It's really, really bad. Right? These networks are bad. They're super bad at modular arithmetic, but they're bad at counting, like basic things. Yeah, just adding things up is they're really bad at. So like it's really tempting to think that somehow machine learning it can just do everything. It absolutely, definitely can't. And so what it's good at and what it's bad at is actually I think an interesting. I don't know whether you're going to get a mathematical answer to this, but even like an approximate answer, what sort of functions f can it learn? I find very hard to say actually. And so therefore why it works is a really interesting thing. Yeah, I think it's an interesting area, but I think it's difficult to come up with hard mathematical reasons.
Okay, and connected to this, and just as a last question, unless someone else wants to add something afterwards. Today I was discussing with a colleague very shortly about the role that perhaps the machine learning should have in the curriculum of a bachelor's degree. So what's your viewpoint on this? Do you think we are passing like a bit of a hype on machine learning, or you think it's coming here to stay, and then we have to somehow make some adjustments to the contents of a bachelor's degree in math, say?
Well, that's a good question. So, I mean, I'm sure this is true around the world, but certainly here in Oxford, any undergraduate lecture course that mentions the word machine and learning has like 5 times as many students in it as anything else. Right? So there is undoubtedly demand, and whether we like it or not, I think students want to know about it. I do also think that there's a real role for mathematicians to explain it on a more conceptual basis. On the other hand, a lot of machine learning is just practical, and I think it's the sort of thing that's best viewed from a mathematical point of view, but also viewed as like something that almost like an engineering or computer science point of view, that actually these are tools that one should learn, but understanding them, what's going on underneath them, I think is important. So I really do think they should be in an undergraduate curriculum. And actually, to be honest, market forces will dictate that. Right? You'll see master's courses which will come up, which will be on machine learning, and they'll be super popular. But so I don't view it as hype. I think it's here to stay. I think it, and I think our undergraduates, and indeed our graduates, should be learning about it. And I think it's fascinating. But on the other hand, sometimes, as I say, it's hard to really understand what's going on from a mathematical point of view. I think you have to realize the limits of mathematics when understanding machine learning.
Okay, so thanks a lot. And if there are no more questions, thanks again for your fascinating talk that really showed this how fascinating machine learning can be. So thank you for opening this series, and remember that we'll continue in around 1 month, in 3-4 weeks. Like we have Elizabeth Manch, and in April we'll have Jürgen Jost. So you are all welcome to join us again. So thank you everyone for joining this first Barcelona Mathematics and Machine Learning Colloquium Series.
Thank you.